Today's topic of discussion will be photoelectric effect. Now look at this. We have metals. Now these metals has got loosely bound electrons in the outermost shell. So since electrons are loosely bound to the nucleus by attractive force, these force being weak can be easily removed or excited to higher energy level provided the sufficient amount of energy is being supplied, which must be greater than the energy that binds the electrons to the nucleus. So when these metals having loosely bound electrons are struck by a photon of having sufficient energy, electrons are ejected from the surface of metal. This phenomenon of the ejection of electrons from the surface of metal when a photon of sufficient energy strikes the surface of metal is what we call as photoelectric effect. Now, due to the ejection of these electrons from the surface of metal, these electrons can be moved in a circuit. Because of the flow of these electrons, the current can be generated, hence the name photoelectric. Electricity due to the electrons coming from photon when photon strikes the surface of metal. Now this photoelectric effect, this is widely used in solar cells. If you look at the solar cells, in solar cells we have a plates. These plates are made up of metals having low ionization energy, means energy required to remove electrons are less. So when these plates are placed in sunlight, sunlight consists of a number of wavelengths. So the energy, some of the energy from the photon will be transferred to the metal, and this energy is used to break the attractive force between the nucleus and the electrons, and hence the electrons are ejected from the surface. Now these electrons is made to flow in external circuit. Due to the flow of this circuit, current is generated, and that current is being stored in a battery. So when the light is cut off, the energy which was stored in the battery is converted again into electrical energy. So this is what we call as photoelectric effect. Now look at this photoelectric effect. So let me give you the definition first. The phenomenon of ejection of electrons from the surface of metal when a photon of sufficient energy falls on it. So this process of ejection is what we call as photoelectric effect, and the ejected electrons are known as photoelectrons. Ejected electrons are known as photoelectrons, and these photoelectrons is responsible for electric current generation. So we have a metal surface. To this metal surface, photon of sufficient energy strikes, and because of this, electrons are removed from the surface of metal. That is what we call as photoelectric effect, and the electrons that is being ejected from the surface is what we call as photoelectrons. Now there are some laws which governs this photoelectric effect. So laws which governs this photoelectric effect. So let's take this first law. Now we are saying that photons are striking the surface of metal and electrons are subsequently ejected from the surface of metal. So there is no time lag between the strike of the surface by photon and the ejection of electron. That means the moment photon strikes the surface of metal, electrons should be simultaneously ejected. So there is no time lag or no time gap between the photon strike and the ejection of electrons. No time lag or gap. No time lag or gap between the photon strike and ejection of electron. That means the moment photon strikes the surface, electrons will be simultaneously ejected. This doesn't mean, look at this, when photon strikes the surface of metal, the energy of the photon is transferred to this electron and electron will undergo some wave type dance. So this is not possible. The moment this photon strikes the surface, energy is transferred and immediately electron should be removed from the surface of metal. The second law which governs this photoelectric effect is, we are saying electron is being ejected by photon. Now look at this. One photon will only eject one electron. So there is no possibility of a one photon ejecting more than one electron. So one photon at a time will eject one electron. So second law says one photon will eject only one electron. So this is 1:1 ratio. So we cannot eject two electrons by one photon, because one photon is carrying one specific energy which is required to remove a single electron from the attractive field of the nucleus. So one photon has to eject one electron. The number 3, now look at this. When photon strikes the surface of metal, the energy of photon is simultaneously transferred to the electron. Now when this energy is transferred to the electron, that energy, some of this energy is used to break the attractive force, or which is known as the binding force, the force which is nucleus and electrons are bind together. So some of the energy is used by this electron and used for breaking this binding energy, and the rest of the energy is carried by electrons in the form of its kinetic energy, because electrons are ejected from the surface. So electrons are moving with a certain velocity. So since electron is moving with certain velocity, these electrons must be having some kinetic energy. So the excess amount of energy that is being converted into the kinetic energy. So this kinetic energy of the ejected electrons, or the velocity, depends on the frequency of incident photon. So if the frequency of incident photon is more, energy is more, minimum energy being fixed, the excess energy is converted into kinetic energy. So the kinetic energy of the electrons, or the velocity of electrons, depends on the frequency of the incident photon. So kinetic energy of ejected electron, or velocity. Kinetic energy or the velocity of ejected electron is proportional to the frequency of incident photon. So means kinetic energy of ejected electrons depends only on the frequency, and this is independent of the intensity of the light, and is independent of the intensity of light. Intensity means brightness. So intensity or the brightness has nothing to do with the energy or the velocity of the ejected electron. This kinetic energy depends only on the frequency of the incident photon. Then number 4, now we are saying if photon is striking the surface of metal and some of this energy is used to break the binding energy. So if the frequency or the wavelength of the photon is less than the energy required to break the attractive force of the electron and the nucleus, then the ejection of electrons won't be possible. That means for these electrons to undergo ejection from the surface of metal, this photon, striking photon, must have minimum amount of energy, and if the energy is less than the minimum amount of energy, then no photoelectric effect will take place. So that means this ejection is possible only when energy is greater than the minimum energy, and this minimum energy which is required for these electrons to undergo ejection, that is what we call as work function or the binding energy or threshold energy or critical energy. Photoelectric effect occurs only when energy of photon is greater than some minimum energy. So this photoelectric effect will occur only when energy of the photon, striking photon, is greater than some minimum energy. So this minimum energy required for this photoelectric effect to occur, this minimum energy is known as work function. So this work function is sometimes given as binding energy, because this is the energy by which electrons are bound to the nucleus by some attractive force. So once this we are supplying energy greater than this binding energy, that electron will be completely free. So once electron is completely free, so this can undergo ejection. So we have to supply some energy which is known as minimum energy, called work function, which is also known as binding energy. This is also known as critical energy. So we have different terms, different for the same energy we have different terms used, which is also known as threshold energy. So energy, minimum energy, which is known as the work function or the binding energy or the critical energy or the threshold energy. So for photoelectric effect, the energy of striking photon should be greater than this energy, and this energy we define this by WO, or sometimes this is defined by this phi. So this WO or phi, this defines the minimum energy required for this ejection. Now look at this. Suppose we are having a metal, we are having metal gas. So this metal, in its outermost shell, some electrons are present which is loosely bound. So nucleus is positively charged, electrons are negatively charged. So between this oppositely charged force, there is some attractive force. So we have to supply energy greater than this attractive force. So when this is being supplied by energy H nu, so means you are supplying energy which is known as work function. So because of this energy, this metal is converted into plus electrons are ejected. So now look at this, you are supplying energy, some minimum energy which is known as work function, binding energy or critical energy or threshold energy. So look at this is what we call as minimum energy. So now look at this, if you look at this equation carefully, we are having neutral isolated gaseous atom Now from this neutral isolated gaseous atom we are removing an electron. So the process of removal of electron from a neutral isolated gaseous atom, so this energy is sometimes known as ionization energy. Means energy required to ionize a neutral isolated gaseous atoms into its ions. So we are supplying energy which is corresponding to ionization energy. So this energy is sometimes defined as binding energy, critical energy, threshold energy, or some minimum energy. So energy of this striking photon should be greater than this minimum energy. Now look at this, we have this energy which is known as work function. So this energy, according to Planck's equation, this energy is related to frequency of incident light, or the frequency of light, or the frequency of photon. So the frequency corresponding to this minimum energy or the minimum frequency of the photon which is required for this ejection of electron is known as threshold frequency. So now look at this, for this ejection, now look at this W naught work function is equals to L nu naught. So now look at this, if I am saying energy must be greater than this work function, then this work function is equals to x nu according to Planck's equation. So this mu naught is greater than is known as threshold frequency, which is also known as critical frequency. So that means the frequency of the incident light or the incident photon should be greater than this threshold frequency. If the frequency of incident photon is less than this threshold or critical frequency, then no photoelectric effect takes place. So therefore, for photoelectric effect to occur, means for ejection of electrons, this incident photon must be greater than this minimum frequency which is known as threshold or critical frequency. This is the frequency of incident photon, this is the frequency of minimum frequency required. So at least you have to supply this minimum energy or greater than this minimum energy. So means photoelectric effect occurs if energy is greater than this minimum energy, which is given by different terms. Now for this minimum energy we need to have a minimum frequency, and this minimum frequency is what we call as the threshold or critical frequency. Now we are thinking now this frequency is related to the wavelength, so we say hc by, so now look at it, this is the minimum frequency, this is the minimum frequency required. So frequency and wavelengths are related. So if this is the minimum frequency, then this lambda, this is the maximum wavelength. So maximum wavelength required for this ejection of electron is lambda naught. So frequency requires minimum, then the wavelength required should be maximum. So this photoelectric effect occurs only when this condition is satisfied. Now then look at this, the moment this photon strikes the surface of metal, electrons are ejected. So how many electrons will be ejected? For a photon of a particular frequency strikes has nothing to do with the frequency of incident light, but the number of photoelectrons or the photoelectric current depends only on the intensity of the incident photon. So as the intensity or the brightness of this photon having some minimum frequency is more, or intensity is more, then the number of photoelectrons ejected will be more. But if the brightness is decreased, or the intensity is decreased, then the number of photoelectrons ejected will be less. So the number of photoelectrons ejected ejected, which is also known as photoelectric or photoelectricity, depends only on the intensity or the brightness of light and is independent of the frequency of incident light. So we are having these are the laws which governs and the photoelectric effect. Now we are saying energy of incident photon is transferred to metal, and some of this energy is used to break this binding force, and the rest energy is converted into the kinetic energy of the ejected electron. So invoking the principle of the conservation of energy, we have from conservation of energy, you have look at this energy of incident photon should be equals to work function, that is the minimum energy or the critical energy, plus the kinetic energy of the ejected electron. So some minimum energy is used for this breaking of this attractive force, and the rest energy is converted into the kinetic energy of the electron. So this is the maximum kinetic energy that could be obtained. So now look at this. So energy of incident photon, so let's say this is capital E, which is equals to the work function plus the kinetic energy. So we say this is the maximum kinetic energy that could be obtained. So now look at this, we have E, energy is equals to h nu according to Planck's equation. So we have, look at this, this is h nu naught plus kinetic energy. So we have kinetic energy maximum. So therefore the kinetic energy maximum kinetic energy that could be obtained is equals to h nu minus nu naught. So if this is the maximum kinetic, so now the basic equation is this. So once we have this minimum frequency and frequency of incident light, we can easily define what is the maximum kinetic energy that could be obtained. So let's say this is equation 1. So kinetic energy, we know kinetic energy is half into mass into velocity. So this is the maximum velocity. So where this m is the mass of electron, because we are dealing with the ejected electrons. So mass of electron into velocity of electron square into half, that is the kinetic energy. So this equals to h nu minus nu naught. So from this we can also define what is the maximum velocity. So velocity maximum will be equals to 2h divided by m. So cross multiplication, nu minus nu naught now under the root. So to define the maximum velocity, again we need to have look at this frequency of incident photon, minimum frequency, mass of electron is always a constant. So mass of electron is 9.1 into 10 to the power minus 31 kilogram. H Planck's constant is 6.6 into 10 to the power minus 34 joule second. This is the constant, so we need to have these values. So let's say this is equation 2, this is equation 3. So now look at this, we can define the velocity as well as the maximum kinetic energy. Now sometimes instead of this frequency, we may also given the wavelength of incident photon. So we have this instead of frequency, this kinetic energy maximum can also be written as h. Nu is c by lambda minus c by lambda naught, or we can say this is hc 1 by lambda minus 1 by lambda naught. So this is the wavelength, this is the minimum wavelength which is required. So kinetic energy, that is half mv maximum square is equals to hc 1 by lambda minus 1 by lambda naught, or look at this v maximum velocity can be written as twice hc by m 1 by lambda minus 1 by lambda naught square root. So we have this. So now look at this. This is the basic equation. From this we can derive what is, if suppose work function and kinetic energy is given, we can define what is the minimum or what is the incident energy. Or if now look at this, incident energy and kinetic energy is given, we can define what is the minimum energy or the binding energy. Or if the binding energy and this energy is given, then also we can define kinetic energy. Once we define kinetic energy, we can define the maximum velocity of the ejected electrons. So either in terms of frequency or in terms of wavelength of light, we can have the equation. Now one more thing that we have to keep in mind is, now sometimes we use a term stopping potential. Stopping potential V naught. This is nu, this is V, or sometimes Vs, stopping potential. Now when when photon strikes the surface with some energy greater than minimum energy, electrons are removed from the surface of metal. Means electrons are moving in the external circuit. Now to stop this movement of electron, if suppose we supply some energy from external source, so that there is no ejection of electrons or no flow of electrons, so that minimum force, that minimum potential, that must be supplied so that there is no flow of electrons or no electron should eject from the metal surface. So that potential is known as the stopping potential. Potential required just to stop ejection of electrons from metal, or we say potential required to stop photoelectric effect from the surface of metal. So that potential that must be supplied so that no electrons undergoes ejection from the surface of metal is known as stopping potential. So electrons are ejecting with certain energy के साथ remove कर रहा है. If you are supplying some potential, so there is no ejection of electron. So the minimum energy जो supply किया that must be equals to this kinetic energy. So therefore the kinetic energy is equals to EVS. Why this is the stopping potential, E is electronic charge, so kinetic energy which is equals to half m V maximum square, kinetic energy maximum, so E is electronic charge. So this is the meaning of, so sometimes stopping potential may be given to you. So once the stopping potential is given, that means indirectly the kinetic energy of the ejected electron is being given, which is equals to E into Vs, stopping potential. E is electronic charge, which is equals to 1.6 into 10 to the power minus 19 coulomb. So this is the value of E, electronic charge, charge carried by one electron. So this is the stopping potential. So now look at this. We have this equation, various forms of equation. So in this form we can say we have this kinetic energy. So look at this equation from equation 1. Kinetic energy is equals to half mv square, which is equals to EV. So from equation 1 we can have EVS is equals to H nu minus nu naught, or we can say this stopping potential is equals to H by E. H is a constant, E is also constant, nu minus nu naught. That means we can have various forms of this photoelectric wave. Different equation is the same. Main equation is energy of incident photon is equals to work function plus kinetic energy. These are different forms of the same equation. So this is in terms of stopping potential. So if you look at the stopping potential, depends on the frequency of incident light. This is in terms of stopping potential. This is the maximum kinetic energy. This is maximum velocity. This is in terms of wavelength of light associated. So now let me give you some graph corresponding to this photoelectric effect. So we have this minimum, this equation. Or let me take this graph. So look at this equation 2. We have this. This is the frequency of incident photon. This is kinetic energy. The variation of kinetic energy means indirectly we are seeing velocity. Now, if look at this equation, if incident photon is having frequency 0, then kinetic energy is minus h nu naught. So we have this. This is 0 value, this is positive value, this is negative value. So at frequency 0, we have this value, that is h nu naught. Now as the frequency nu increases, difference between these two terms decreases. As the distance decreases, this value will increase, and this goes to this particular point. At a certain point of time, we may have this nu equals to nu naught, so the kinetic energy will be 0. Above this point, the value of nu is greater than nu naught, so this increases here. So this particular point, this represents the minimum frequency which is required for the ejection of electrons. Now if you look at this graph, this is equation of straight line with slope equals to h. So now look at it. If suppose this is theta, then this slope is equals to tan theta. So this slope is equals to h. So once we have the slope, we can define the value of h. H is the slope. So if you look at this, the kinetic energy increases as the intensity of as the frequency of incident photon increases. So instead of this, we can also have wavelength. So this kinetic energy has nothing to do with the intensity of light. So suppose we have this. This is kinetic energy of ejected electron. This is intensity of photon. Then this value is always constant, because we already say in kinetic energy depends only on the frequency of incident photon, not on the intensity of photon. But on the other hand, look at this, we have number of photons ejected or intensity. So intensity versus photo current, electric current. Photoelectric current means number of photons ejected. This increases. So as the intensity increases, number of photoelectric current increases, but the kinetic energy remains unchanged. The same, look at this, we can also write down here. This is frequency, this is photoelectric current. Photoelectric current. Now this photoelectric current has nothing to do with this frequency. So this remains constant. So photoelectric current is independent of the frequency but depends on the intensity. As the intensity of the light is increased or the photon is increased, the photoelectric current also increases. So this is the graphical representation of photoelectric effect. So now because of this requires the energy that binds the electrons to the nucleus should be low. If the energy is low, simply supplying a very small amount of energy, electrons can be ejected. Because of this only, the alkali metals like potassium, rubidium, cesium, these elements are extensively used in the solar cells. The reason being the ionization energy or the binding energy or the work function of these elements are very small. So this is photoelectric effect. Now let me give you some example how to use this equation in solving problems. Now look at this problem. Minimum frequency required for ejection of electron is given as this. Frequency of incident photon is given here. So we have to find the kinetic energy of the ejected electron. So we have this photoelectric effect from which we have kinetic energy is equals to S nu minus nu naught. So now look at this. H is 6.6 into 10 to the power minus 34. Nu is given as 1 into 10 to the power 15. So we can say 10 into 10 to the power 14 minus nu naught is 7 into 10 to the power 14. So we say look at this 6.6 into 10 to the power minus 34 into 10 to the power minus 14. So 10 minus 7 is 3. So we have this. This is the kinetic energy of the ejected electron. Simply look at this. We have given mu and mu naught. So just take this difference multiplied by 8. That gives you the kinetic energy of the ejected electron. So this is positive. So this much amount of energy is possessed by electrons that is being ejected from the surface of metal. So look at this. Now a light with wavelength 450 nanometer strikes the surface of metal. The work function of that metal is 2.16 electron volt. Calculate the velocity of the ejected electrons. So now look at this. Question says velocity. So we have to find the kinetic energy. So kinetic energy is energy of incident photon minus the work functions. Already work function is given as 2.16 electron volt. We have to find this energy corresponding to this wavelength. Now from this kinetic energy we have to find the velocity. So kinetic energy is half m v maximum square, which is equals to E minus W naught, or we can say the velocity of the ejected electron is twice 2 by m E minus W naught square root. Now W naught is given as 2.16 electron volt. So we have to convert this in terms of joule. So 1 electron volt is equals to 1.6 into 10 to the power minus 19 joule. So 1 electron volt is equals to 1.6 into 10 to the power minus 19 joule. So we have to keep in mind. So 1 electron volt is 1.6 into 10 to the power minus 19 joule. So we have this energy. Now we have this E. So this E is equals to hc by lambda. So h is given as 6.6 into 10 to the power minus 34. C is 3 into 10 to the power 8 meter per second. Speed of light divided by wavelength. Wavelength is 450 nanometers. So we have 450 into 10 to the power minus 9 meters. So this is the energy of incident photon. We have work function. So we'll just replace the value of this E and the work function here. Multiplied by 2 by m. Mass of electron. Mass of electron is 9.1 into 10 to the power minus 31 kilograms. So we have all the values. So just by using this we can easily find the velocity. that is the velocity of ejected electrons. So why I am giving this example, because this work function is expressed in terms of electron volt. So electron volt should be converted into joule. 1 electron volt is equals to 1.6 into 10 power minus 19 joule. So by this we can easily replace the values here. E minus E naught into 2 by m. M is always a constant, 9.1 into 10 power minus 35 kilogram. The next question says, the voltage required to stop the photoelectric effect from the surface of a metal is 0.24 voltage when the radiation of wavelength 254 nanometers strikes it. Calculate the work function. So first of all, look at this. We have given stopping potential. So stopping potential is given as 0.24 volt. So therefore kinetic energy is equals to E into stopping potential, which is equals to 1.6 into 10 to the power minus 19 into 0.24 joule. So we have this energy. Now we have this incident photon light. Incident photon is hc by lambda. So h is 6.6 into 10 power minus 34. C is 3 into 10 to the power 8 divided by wavelength is 254 nanometers. So we have 254 into 10 to the power minus 9 meters. So this is again joule. So we have kinetic energy, we have incident photon. So therefore work function is equals to energy of incident photon minus work function is minus the kinetic energy. So we have this. So simply you have to take this, simplify this. 6.6 into 3 divided by 254 into 10 to the power plus 9, 8, 17. So 10 to the power minus 17 minus 1.6 into 0.24 into 10 to the power minus 19. So this will give you the work function in terms of joule. So this is how we convert this stopping potential into kinetic energy. So kinetic energy is E into stopping potential is 1.6 into 10 to the power minus 19. This is the stopping potential. So we have energy in terms of joule, and energy of incident photon is hc by lambda. So lambda is given as 254 nanometers. So this is how we use stopping potential. Now look at this next example. So when a radiation of 300 nanometer wavelength falls on sodium metal, electrons are emitted. Means we are undergoing photoelectric effect. Having kinetic energy 1.6 at into 10 to the 5 joule per mole. Calculate the minimum energy in kilojoule per mole joule per mole required for this process. So now look at this. Electrons are removing from the surface. So the energy required for this process, that is what we call as the binding energy, because we are removing electrons from a neutral isolated gaseous atom. So we have this binding energy. So this binding energy is nothing but the work function. So the minimum energy required for this process is nothing but the binding energy, which is known as work function or critical energy. So kinetic energy is given, frequency of incident photon is given, but one thing that we have to keep in mind is this is the energy corresponding to one photon, but kinetic energy is given as 1 mole. Energy required for ejection of 1 mole electron, but यहाँ से क्या मिलेगा? Energy of single electron. So we have to convert into mole energy. So now look at this energy of single photon is equals to hc by lambda, that is 6.6 into 3 into 10 to the power 34 8 minus 26 divided by 300 into 10 to the power minus 9. So this can be 6.6 into 7 cancel out 10 to the power minus 17 joule. Now this is energy of single photon. So energy of 1 mole photon. 1 mole photon, because energy is given in terms of joule per mole, energy for 1 mole. So energy of 1 mole photon is this energy multiplied by Avogadro number. So we have 6.6 into 10 to the power minus 17 into 6.02 into 10 to the power 23. It is joule per mole. So we can say 6.6 into 6.02 into 10 to the power 17. And so this is 6 joule per mole. So we have in one energy of 1 mole photon, we have kinetic energy of 1 mole ejection electron. Now we have to find the binding energy. So therefore energy required for this process, which is nothing but the binding energy or the ionization energy. So this work function is equals to energy of photon minus kinetic energy. So energy of photon is here 6.6 into 6.02 into 10 to the power 6 minus kinetic energy, that is 1.68 into 10 to the power 5. So this is energy of photon. So this energy must be in terms of joule per mole. Now we have to convert this into kilojoule. So once we have this, we can easily convert into kilojoule. So this is, so now look at this. Why I am giving this example? Because look at this. This is energy of single photon, but that energy is given as per mole. So we have to convert for 1 mole of the photon. Only then we can undergo this addition subtraction here. Look at this next problem. A wavelength 400 nanometer is incident on the surface of metal having work function 2.28 electron volt. What is the longest wavelength which can result in the emission of photoelectrons? So now look at this. We have minimum energy required for photoelectron is given as h nu, or sorry, work function. So therefore look at this, work function is h nu. So this is the minimum frequency required for this ejection of electron. So if frequency is minimum, then the wavelength should be maximum. This is the maximum wavelength required for ejection of electrons. So therefore the maximum wavelength is equals to hc by work function. So now h is 6.6 into 10 to the power minus 34, c is 3 into 10 to the power 8. Now work function is given as electron volt, so convert in terms of joule. So 2.28 into 1.6 into 10 to the power minus 19. So this is the meter. So this is the wavelength of the photon, maximum wavelength of the photon required for this ejection of electron having this work function.